Okay, in the last lecture, I went over kind of this longer version of, well, what's this all about? So hopefully that's useful, but what's for most people really is the focus is, I'll try to highlight, okay, is right here. We're trying to find, let's say the 95% confidence interval. We have the sample mean, where that's p hat or x bar, and then plus or minus about two standard errors, where the standard error is defined for proportions down here. For continuous variables, it's the standard deviation from the sample divided by the square root of n. So I'm not going to go through this example. This was like 4.5 years ago now. Let me go on to the fourth page here. So a little modern art or Japanese art or something, I don't know. But okay, anyway. So just a little bit more idea of what's going on here, because there's a lot of people there's this standard deviation and standard error. Some people, error deviation, isn't that the same thing? No, it's not. Okay, so here is focusing on the graphs here on the right. Okay, admittedly not the most beautiful things, but if we were looking at distribution of salaries, okay, so some people are making maybe 0 or 10,000, maybe not 0, but 10,000, 20,000, all the way up to 60, maybe even higher. And those are each of these, this is kind of like a bar chart if you actually had done it that way rather than a nice smooth, somewhat smooth curve. And it doesn't have to be, it could be skewed by the central limit theorem. Just one more reference to that. So these represent, though, individual, like at the middle here, if we had 100 people, there might be 10 or 15 that are around 40,000, then 8 or 9 that are at, say, 50,000, and so on and so forth. When we sample this, though, if we're looking at 100 at a time, we're going to find a much tighter distribution. If we ask 100 people, college graduates, what their salary is, we're not going to find an average of $60,000 or 70,000 or 5,000, hopefully not anyway, if the true average is around 40,000, okay? So yeah, within that sample, we're going to get some high ones, but with 100, there's going to be quite a bit of averaging, so to speak. So by chance, still, yeah, occasionally we might get 43,000, we might get 38,000, but we're not going to get the extreme values if we only ask one person. So that's the idea here. As I'm thinking about it, for your case study, yeah, you can come up with, well, what's the 95% confidence interval for some of the more important variables in your study. Okay. The second part of this is about hypothesis testing, which is very similar. So basically it's, well, let me just go through it here. So here's some examples. So usually an hypothesis start with a claim outside of the data set. So someone claims, maybe at Asbury, that the average Asbury grad starting salary is $41,000. And they may have based that on past data or experience or just kind of a sense of talking to people. So then we want to come back with data, though, a new data set, and we want to test that. So our null hypothesis, it's an H0 or H null there. So mu, and like, what is this? Okay, so that's the Greek letter mu, it looks like a U. That is what we claim is the true population mean. If we in fact knew everyone's starting salary, it would be equal to 41,000. The alternative hypothesis is that the true population mean is not equal to 41,000. Okay. So the steps here, well, first of all, I think I'm just doing a confidence interval here. So a 95 confidence interval amount around the true mean, not x bar. So that's a little bit different than our regular confidence interval. Is 41,000 plus or minus, again, this 1.96 is the 95% z value. And the standard error here, I think, where did I get that from? Must have been from the sample like S over the square root of n. So that's just given to us there. The idea here is, and then you come up with this range here, so it's just over 39,000 to just over 43,000 is a 95% confidence interval around what we claim, this 41,000 average. The idea here is, well, part of it anyway, is, well, even if, if I claimed it was 41,000 and you did all this and found it to be 41,005, hopefully you wouldn't go off and be like, no, this is an outrage. This is, for one thing, it's a little higher, which is good for Asbury, I guess. But it was a penny higher. If it was even a few $100s off, you probably wouldn't be like, oh no, this is ridiculous. We can't expect it to be to the penny correct. If that was true, then we're probably fudging our data numbers. So there's this pretty wide range. It's not super wide, but yeah, any between essentially 39,000 and 43,000, about plus or minus 2,000 either way, would still be, we would be 95% confident, yeah, that's just sampling error. So if then we come back with our X bar, remember we centered this around our claim, if the sample data, the evidence falls into this confidence interval, then yes, we cannot reject H-notch. So if we got, 40,000, if we got 42,800, that's kind of close, but technically it's within the acceptable reason that we cannot reject our claim. If it is 39,000 or 35,000 or 50,000, then we do reject the claim. And we'll see these steps over and over. Okay, let's go down to another question here. Sometimes, so that was focusing on a very equal one number. A lot of times there's directional, so a claim the average salary is at least 41,000. So a little background here. Again, you might think, well, this is pretty simple. We don't need to do all this stuff, which I've done. But so since I've done it, you might sense, well, yeah, there's something more here. The idea here is, and I go through some of this when I talk a little bit more about hypothesis testing, is that the null hypothesis is given the benefit of the doubt. So the analogy is if someone is in court or being sued or prosecuted for some crime, they maintain their innocence as long as there's not overwhelming evidence to the contrary. So even though it may look like someone robbed the bank, unless you can be within a shadow of a doubt, you're not supposed to put that person in jail, okay, by whatever legal standards anyway. So similarly here, it may seem kind of strange to say, all right, well, if you claim it's greater or equal to 41,000 and I find it to be 40,950, you're wrong. It's actually just a little bit lower than that. But because there's this precedence given to the claim, we can actually go a little bit lower than 41,000 and still maintain that the claim is valid. So there's some philosophical, theoretical reasons to maybe debate that idea, but this is how it's done in at least what's called classical statistics. So here we have a one-sided test. We're going to find the 95% confidence interval around mu again. Now, since it's one-sided, we need a smaller z-value. So it's going to be 41,000 minus 1.645. So now anything from 39,355 up to infinity, you really can't. Salaries probably don't add up to infinity. But even if it was 100,000, you'd be like, well, you claimed it was over 41,000 and made a very conservative claim. Same idea though. So once we get at that confidence interval, we just check, does the sample mean the evidence, using the court analogy or the prosecution analogy, does the evidence agree then with that? Does it fall within that range? If so, accept the null hypothesis or cannot reject it. If not, then reject it. Okay. All right. Ignore these. I think these chapter numbers, they may be from the Shaw's guide, but if not, then there are some pretty good examples of this and more in the Shaw's business statistics. So um, a classic example, and you may be able to do this for your case, is comparing two group means. So there's some assumptions about independence and normality, and you can, large sample size. You can read through that. It's very similar to before. Now that we have two sample averages, and then usually you can test. You could say the difference between male and female salaries is $10,000. You could claim that. More commonly, we're looking for equality. So we're saying across genders, there's no salary statistical difference, or across a medical test, there's no difference between the experimental group and the control group. Um, so here is an example, and it looks a little bit clearer. Oh, that's a lot of stuff here, but this top part here is just, well, not all information, but okay. So this part here would be, well, from the raw data set that we had two samples, 1,000 men where their average salary was 50,000 with a standard deviation within that, within the male workers of 5,000. And then for some reason, we only surveyed 500 women. They don't have to be equal. Then what we're interested in, the Y2, it looks like it's less. It's 48,000. And the standard deviation within the women's salaries was 10,000. So the standard error is given as so for looking at two different groups. The two standard deviations squared divided by the two sample sizes. It's 474. This is really the key here in terms of, cut it off a little bit, but anyway, all right. Oh, okay. So the difference is 2,000, but we're given this fudge factor of plus or minus 1.96 times the standard error, which we just found up here. All right. So we go down here. Okay. Well, there's actually two parts to this. Let me back up here a second. So what this is here is saying, well, again, there's two parts to this whole kind of book here, this lecture three-part series, I think it will be. So the first part would be the 95% confidence interval. So it's the point estimate is there's a $2,000 difference. If we say, well, there is some sampling variability, well, then we could say with 95% confidence is between 1,070 and 2,930. So you already got a sense, though, well, if that's a 95% confidence interval, when we do it just slightly differently around the expected mean, we're still going to find that there appears, because these are pretty large samples, that $2,000, that's enough variability to suggest there's something else going on here, whether it's bias, whether it's men are smarter. Just kidding. Okay. Anyway, I don't want to go down that path in any day now. Anyway, so here again, so the claim is that the two means are equal. Another way of saying that is mu1 minus mu2 equals 0. And the alternative is that they're not, that there is some statistical difference. It doesn't explain, well, what caused it. Is it, again, is it bias, or, these can be pretty tricky to measure to get. Anyway, okay, oops. So the 95% confidence interval around the claim, which is 0, is now 0 plus or minus 1.96 times the standard error. So there could be within plus or minus $930 difference between the two groups, and we've got to say, well, that's fine, that's close enough. It's not $5, $100, $500, $900, okay, $930, okay. But then it goes, 1,000, or in this case 2,000 difference. We need to reject the null hypothesis that men and women in this industry or whatever it was do not earn the same money. Okay. I think I'm going to pause there and come back with a final grand finale conclusion.